real-time operating system. They factored the monolithic code into sort of glue code that connects the various pieces together, and then control system code like stability and communications code that runs on top of the glue code. And those two pieces were written in a domain-specific language that we'll hear about in the next few slides that made it so that that code was high assurance. And so the legacy code is getting smaller. And then at the 16-month period, they switched out the FreeRTOS for Dicta Z Chronos that at this point has had some but not all of the correctness proofs done about it that you would expect. The glue code is sort of partially high assurance because it's being generated from a high-level specification, and more and more of the legacy code has been converted to being generated from these domain-specific languages. So we gave that system back to the red team. That system has almost all of the capabilities and functionality of the original quadcopter. In particular, it has stability control, altitude control, directional hold, and a denial of service detection capability. Basically, it monitors to see if somebody's trying to break in, and if so, it detects that there's a denial of service attack, and it responds in a sort of mission-specific way. One of the things that's really difficult about denial of service kinds of attacks is there's no single right thing to do. Like, what should you do if you know that you're not getting all the communication you should? It kind of depends, right? If you're in hostile territory and what you really care about is the enemy doesn't get access to your technology, well, then maybe self-destructing is the right technology. If you're, flying, if you're Amazon delivering packages, self-destructing is probably not the right thing to do. The system almost has GPS waypoint navigation. About 80% of it is implemented. They're continuing to work on this, and I'm told that shortly it will have this capability. Then Rockwell Collins proved system-wide security properties, drawing upon properties of the sub-pieces of the system, so drawing upon properties of the code that Galois was producing for controls and the code that NICTA produced for the operating systems. They proved particularly the system is memory safe, that the system ignores any malformed messages, that the system ignores any non-authenticated messages. Basically, if it's a malformed message or a non-authenticated message, it just drops it on the floor and does nothing with it. And then it proves that all good messages, so ones that are not ignored because of being either malformed or unauthenticated, that are received by the quadcopter will be acted upon. So it can't prove that all messages sent by the ground station are acted upon because you could be jamming the communication network and so the message could not be received, and that would be handled by the denial of service kind of part of the system. So that system was given to the red team. The red team had 6 weeks with the source codes. They were able to see all of the code in the system, and at the end of that time, they were not able to remotely break in and take control over the system, which is an amazing result. My colleague at DARPA, who is an expert in penetration testing, that's what he's done for the last 12 years before going to DARPA, his assessment is that this quadcopter is the most secure UAV on the planet, right? Which is kind of scary if you think about it. But also a good sign for going forward. And the slide here shows the URL where you can go and download all the code that they've been using. Okay, so just diving in a little bit to the technical work. So Rockwell Collins is the team that is the group that's leading the ground team. They're responsible for the whole system integration and proving the system-wide properties. The approach that they've taken to doing that is using an architecture-based approach. They've been using AADL, which is a language for specifying the architecture of a system. It allows them to describe both the hardware and the software of the system and connections between them. This is their solution to the problem of composition. How do you get a system-wide property when you can't just slice the system-wide property into smaller pieces of the same property and push them down to the whole system? They use the architecture to say, well, if this is the property we want at the top level, that means at the next level down, this piece has to have that property, this piece has to have that property. They use a assumed guarantee reasoning infrastructure to be able to put those pieces together to get the system-wide properties out of those pieces. They have multiple levels of abstraction, so as you go down the hierarchy, you can break this complex piece into smaller pieces and continue all the way down the system, so you can choose to work at whatever level of abstraction is the appropriate one for whatever property you're trying to prove. They've developed an annex to AADL. So AADL is just a way of describing hardware and system. It has vocabulary for hardware, it has vocabulary for software. It doesn't have a formal semantics associated with it, so they've developed an annex that allows them to give a formal semantics to the system. They've built the agree tool for doing that compositional reasoning, and they've built the resolute tool, which is a architecture-based assurance case argument. So in this kind of domain, people are responsible for producing what they call assurance cases, which at the top level is why do we think the system is going to do what it's supposed to do. They've mostly been focused on safety kinds of properties, but they're being adapted these days for security kind of properties, and that's what Rockwell Collins is doing. Right, so the way the system works is it basically takes a top-level property, and you can specify how that property gets broken down as you go down the architecture, and the tool tracks automatically for you the state of a given property given a given description of the system. So for example, the Rockwell Collins team built a high-level description of the quadcopter based on their understanding of how the system was architected at the very beginning. And then a few months later, as Galwa actually built the software, it turned out the software was in fact a great deal more complicated than the initial model. So they plugged the actual description, the description of the actual system into their tool, and all of a sudden a lot of the properties that we're holding in the simple version no longer held over the actual system, but the tool flagged it for them automatically. Right? For example, one of the properties they talked about was that there was only one way to communicate with the flying copter, but it turned out in the real system there were actually two ways to communicate with the flying copter, one of which was a safety control. And so the property immediately failed, saying, no, this is not true over this architecture. It was a way of sort of automatically detecting that the property no longer held. So it did exactly what we wanted it to do in that case. So as the property kind of gets pushed down the tree, there are various ways in which you can discharge a given assumption. Of course, one of the things you can do is you get down to, say, SEL4, and you have proven properties about the operating system that are machine checked. You can say, okay, I definitely know this property holds, right? Cox says that, or Isabel says that my operating system is memory safe, done. But you might not know that, right? You might not have that kind of a high level of assurance. You might get to a separate piece, and it's like, well, this piece, we've had 3 people do a code review, check, right? So it's like, well, is that as good? No, clearly not as good. But you can do audits and sort of figuring out, why do we know this? How do we know this? But what the Resolute tool does is it gives you a way of talking about this kind of argumentation and tracking it. Oh, right, and then the last thing that the tool does is, by virtue of having this description of the overall architecture, there's a lot of glue code that says how do you connect these various things together. And as always, when you put together pieces, the seams between them is where you get a lot of the problems. And so what the team observed is that we have a description of the architecture and all the pieces. We can generate the code that puts everything together, and we can prove that the pipes are connected properly. And so that's the last piece of what Rockwell Collins is doing, is generating that glue code that connects the pieces together. Okay, so the next part of the team is Galwa, doing technical area 3. So they're responsible for generating all of the sort of application-specific code on the quadcopter, the flight control, the waypoint monitoring thing, the communication infrastructure with the ground station. The way that they've been doing that is creating domain-specific languages embedded in Haskell. One of them is called Ivory. Ivory is a language that allows you to write memory-safe C code in a relatively straightforward way, where that they can use Haskell to basically be a super powerful macro language for putting together the C code. They've also created a second embedded domain-specific language called Tower that is responsible for specifying the components of the system and how they fit together with the process, things like how many processes there are, how the processes communicate with each other, what kind of timing constraints they have, things like that. The people who built that, in fact, have an experience report paper in this conference. It's, in fact, in the next session. Pat is sitting right here, probably wishing that I don't steal too much of his thunder. So if you're curious to hear more about what the Galwa team has been doing and the technology that they've used, I encourage you to come to the first talk in the next session. Basically, they were able to create all of the software from about 10,000 lines of Ivory and Tower code, and then that generated about 50,000 lines of code, which is the code that's flying on the quadcopter now. They also generate a lot of properties that they tried to prove automatically, and they're still working on discharging more of these properties. Right. This is a very impressive piece of work. And then they're building on top of the last level down is the NICTA's operating system pieces. So NICTA, I don't know if you're not familiar with this group, I encourage you to go find out what they're doing. It's an amazingly impressive effort out of in Australia. This is summarizing at a very high level the amazing work that they're doing. So the main piece of this is the SEL4 microkernel. It's about a 10,000 line microkernel that's been proven to be fully functionally correct. It was reported on at SOSP maybe 10 years ago, something like that. They basically proved full functional correctness of the microkernel, and the microkernel is written to be efficient, so it's not slow, it's a fast microkernel suitable for these kinds of applications that's been proven to be fully functionally correct. From the full functional specification of what the system is doing, they've proven integrity, confidentiality, non-transitive interference, intransitive non-interference, kind of the properties that security researchers care about follow from a high-level specification. They've proven that the C code implementation is fully functionally correct, and then they've proven that when you take that C code and compile it down to the binary is correctly implementing the C code. They did that in a really interesting way that was described in PLDI last year. So they didn't use CompCert. Instead, they took the actual binary, they took the C code, and they used model checking to connect them up so that they could prove not that the compiler was correct, but that in this one instance, the compiler was correct. They have periodically tried to use CompCert, but they need one compiler optimization that is not currently in CompCert. And without that compiler optimization, the code runs like 2 to 4 times slower than it does with the compiler optimization, and that 2 to 4 times performance hit is unacceptable to them. So one day we might be able to have the SCL4 compiled with CompCert in a way that's fast enough, but that day isn't here quite yet. All right, so that's the SCL4 work. They're working on eChronos, which is a separate code base for real-time operating system. It's actually a family of real-time operating systems. You have a configuration file that specifies what properties you want, and then they generate from that property description the RTOS that suits your needs. They have about 76 possible different versions, 6 of which they've actually used. They're in the process of proving the same kind of correctness properties that they proved for SCL4, but here they're working on proving those properties in a much more automated way, so lower levels of effort required. Then they're working on device drivers, synthesizing device drivers from high-level specifications. They're working on synthesizing file system from high-level specification. So Gabby, who's in the audience, is working on that piece. I encourage you to talk to her about that. They had a paper at Programming Languages and Operating System Workshop at SOSP this year about that effort. And then the last piece is CamKeys, which is a configuration language which lets you specify how to configure everything. So all of these pieces that I've been talking about have to be configured, and if you get the configuration wrong, then you don't get the properties you want. So how the configuration happens is really important, and CamKeys is a system for doing that configuration. So then the last part of the Air team is Boeing, and what Boeing's job is to take the tools and technology of the rest of the Air team and apply it to their platform and to produce a high assurance version of the unmanned little bird, and symmetrically to summarize the challenges that they're experiencing and report that back to the rest of the Air team so that they can develop their tools in a way that are suitable for Boeing to use. In phase 1, they worked on, so the architecture of the unmanned little bird, there are actually 2 processors. One that is the flight control, the thing that has the very high performance control code for keeping the helicopter flying and navigating, and then a mission control computer that's responsible for saying, go over there, do this, do that, kind of the mission level speed pieces. So they've been porting the software for the mission computer to run on top of SCL4. They got that working in the simulator at the end of phase 1. They're on track for running an actual simulator on the, they're on track for running HACMS code in a real flight demo on a real helicopter at the end of phase 3. In fact, I was talking to John yesterday, and he was saying that they're thinking very seriously about doing a flight demo at the end of phase 2. So we might have HACMS code running on a real helicopter in about 18 months from now, maybe 12 months from now. So that's really exciting. So then, what is the Air team doing now? They are working on re-architecting the quadcopter so that its architecture is more closely related to the architecture of the unmanned little bird, so that the transition to that platform is easier and more realistic. So how are they doing that? Well, they're starting with the quadcopter that they produced at the end of phase 1, and they are revising it so that instead of having one processor, it now has 2 processors. One of them is the equivalent of the flight control computer. The other is the equivalent of the mission control computer. On the flight computer, they're still going to be running the same eChronos real-time operating system, the same kind of blue code that's being generated from the high-level specifications, and the flight control code that's being generated from Ivory and Tower. Then the mission computer has a slightly more powerful processor that's going to be running the SEL4. So I think this level of architecture has been done at this point. All of the team members have this architecture and can run this infrastructure. They're working then towards being able to configure the SEL4 so that it has the mission-specific code that's high assurance, that's responsible for communication with the ground station and things like that. And then separately, you can have a different partition in which you can run Linux and mission-specific things like here's a camera that's filming the football practices or whatever the quadcopter is being used for. We were actually at the Seattle Seahawks training facility, and the Seattle Seahawks people were talking about using a quadcopter to film the team as they were practicing, basically flying over what's going on. So that kind of code that's flying over the football team would be the mission code that would be running in this Linux partition. But at the end of phase 2, the idea is that we'll give the red team full access to that process. So they can put whatever code they want to run in that specific partition, and the goal of the red team would be to be able to break out of that partition and take over control of the quadcopter. So it'll be interesting to see if the SEL4 proofs of isolation really hold when the red team is trying to break out. Right, so that's a summary of the air team, what's going on. I just briefly wanted to come back to this slide to talk a little bit about what the ground team is doing. So the ground team has the same structure where there's the vehicle experts, operating system experts, control system experts, integration, and working with the same red team. This team has a little bit harder task in that they didn't bid as a group. They bid individually on those technologies, and we put them together into this team. So one of the things that they had to do in the first phase was figure out how to work together, which is a very non-trivial task, but they've done a really fantastic job at that. So just to highlight some of the pieces that people in this community might be familiar with, the Princeton, Yale, MIT team is working, so Princeton is working on the ComCert verified compiler. The original system, it was only for a whole program compilation that you got the correctness results. So what they've been working on is proving that separate compilation works, and in fact they recently had that result. They didn't have to change the compiler at all, they just had to change the proof structure, but that was a really non-trivial set of changes to get the invariance correct so that they could prove that ComCert didn't require the whole program. They're working on supporting concurrency in that way as well. Andrew Appel is working on program logics and tactic support in Coq so that you can reason about C code, where then the proof gets pushed down through the compiler to the actual binaries that are running. The Yale team is working on the Certicos, which is a hypervisor, something that's akin to the SEL4 microkernel. They've been making good progress there. The proof infrastructure is going through really nicely. The challenge in some sense is that they don't have quite enough performance. So in this case, they have all these customers, the rest of the ground team saying, we needed to do this, we needed to do this, we needed to do this. And the Certicos team is like both trying to do the proof and trying to satisfy their customers, which is a really difficult challenge. And then Adam Chapala at MIT is working on tactics libraries for Coq to be able to make it so that it's much faster to prove properties about the high-level C code written in Coq in a way that doesn't require Adam or his PhD students to be able to get the system to work. The CNU team is working on taking high-level specifications and compiling it down into very efficient platform-specific code in a way where the compiler tracks the transformations that are done and can prove that the source code is equal to the compiled code, and focused on monitors for control systems in that process. And then Penn is really control system experts. They're focused on generating control systems that are aware of attacks. So for example, like replay attacks are one concern. So they're talking about generating control systems that have known jitter in them. So if you just try to replay the sequence of controls, it will be detected as an attack because the jitter sequence will not match the expected jitter sequence. And they're also working on proving that that compilation path is correct, and Stephanie Wyrick is here, has been working on that piece. Right, so what I've told you about is all the technical pieces, and they've been making really good progress. I would say that we're really on track to being able to show that this thesis of a formal methods-based approach to producing software for embedded systems that's much more secure than in the past is a good one. So that's really exciting. The next set of hurdles are related to tech transfer. This is a huge problem. Like, one of the issues is that we've estimated there are about 1,000 people in the US who have the skills necessary to work on these tools. which is fine when you're talking about a small research community. But when you're saying like every car needs to have this in it, or every flight system needs to have this in it, or every refrigerator needs to have this in it, we're like orders of magnitude away from a workforce that is sufficiently robust to be able to do this. That's just one of the many problems. All of these others are really important and critical as well. But in some sense, all of these things are irrelevant until you have the technology that can possibly solve this problem. Once that we've demonstrated that you have the technology, then these things become really important problems and need to be addressed. So in some sense, these are what's up next. This slide then summarizes some of the more technical issues that still need to be solved or need much more work to focus on. But I am now out of time, so I would be happy to stop here and take questions.
You may have noticed there are two microphones here, and a third one back there. So for anybody who's got questions, if you could please approach one of the microphones.
Matthias.
Kathleen, I think you're working on the wrong
Matthias, could you please, I'm sorry, but otherwise what you're saying will not be on the recording. And thank you.
Kathleen, your penultimate slide suggests you're working on the wrong problem. You should have used a team to come up with a catastrophic event that really demands that we train a lot more people, and that people in universities actually think this is cool work. Years ago, I created a freshman course on proving things correct with ACL2, because the vision was, we would be able to create domain-specific languages in ACL2, prove things about them, and the kids get excited. They don't, because Chain Street makes more money, Amazon delivers more packages, and Google has better search engines. So make it cool.
Right. That's in some sense exactly.
Catastrophic event.
Yeah. So in some sense, like the work that Stefan and Yoshi did are exactly the kind of work you're describing. They're like, wow, you can take over a car remotely. This is really cool. And HACMS is a response to say, well, let's try not to do that.
So I will say we interviewed them. We interviewed part of this team at Northeastern, and the reaction by the students was, okay. So it needs to be more catastrophic.
Right. So sometimes the goal is to be able to get there without creating catastrophic events, which actually is really frustrating in some sense, right? So one of the things that's happening in the US is the Department of Transportation is getting ready to mandate vehicle-to-vehicle communications. So mandate that every car can talk to every other car via a network. Right. Yeah. So you can see why they're doing this, right? It has tremendous safety consequences, right? You'll be able to have cars that are going around corners know what's coming up around the corner if there's another car over there. Or you can see that there's a car that's going to run a red light, even though the driver can't see it because they're talking via the network. So the safety evidence is compelling that this is really a good idea. But it introduces dramatic security consequences. And the group that's in the process of mandating this, right, to mandate something requires just a vast amount of work. And they've been doing this vast amount of work for the past 10 years. And they've produced really careful, thorough documentation on many, many topics. They've talked to many security experts about this. And they've built a really compelling case about the communication security, about privacy. So like clearly they're really, really worried about privacy. They've completely ignored remote code execution. Like they're just not anywhere in their documentation. So I've been talking to them about saying, guys, you can't ignore this, right? This is super important. We know every time you start to network systems, you get this whole other class of problems. You don't want this to happen in your cars. And like, well, it's not happening in practice. And you're just like, oh, of course it's not happening in practice. We've got to solve it before it happens in practice. And you're just like, you can see why people will start to get tempted to like make it happen in practice so that they will do something. Yeah, so hopefully they will actually do something before it happens for real. Next question?
Hi. So you mentioned that one of the trends in these systems relative to desktop security, or to doing security research in desktops, is that the hardware has significantly less resources. And I'm wondering if you have any insight to what's driving those decisions to not, for example, include whatever quad cores or something like that in.
So there's huge price sensitivity in these kinds of systems. So in the auto industry, for example, if an engineer wants to increase the cost of a processor by a penny, they have to get approval several levels up the chain. Because of the scale of what's involved, the costs become enormous very, very quickly, and the industry has very, very small margins. Right? These are not desktop computers where you have huge margins. They're very tightly cost constrained.
Thanks.
Sure.
A quick question to set up my question. How much does this cost?
How much was HACMS research? The $70 million over 4.5 years.
So first of all, this is a cool presentation about cool researchers working on a cool problem. No doubt about that. But you'll be aware that there's a long discussion about do we have free markets or planned markets? Do we have researcher-led decision about what's going to be done? Or is it led top-down by planning? So even though you describe this as bottom-up, of course it's planned. One reason for that is if you go to the politicians and you say, here, you can spend $70 million over 5 years and get high assurance cyber military systems, or you can do whatever the computer scientists think is best, you know which one they'll go for. Nonetheless, there's a debate about which is the best way of spending this, and you're in a good perspective to comment on how we go about making that decision and what the strengths and weaknesses are. So that's what I wanted to ask you about.
Right, so I think both are good, and having both is really good. So DARPA has, in some sense, the top-down, where like I manage the HACMS program, right? I set it up, I decided what the technical areas were, teams bid, and then I keep track of whether the teams are going in the right direction, and they're not, basically if they decided, well, I really want to do this instead, it's like, okay, fine, you can go do that instead, but we still need a group to do this, so we're going to take your money and somebody else will do that instead. But then NSF does the opposite, right, where we're just going to, so I think that it's really good that we have both NSF and something like DARPA, that either one model is not sufficient, either one by itself is not good. You need to have both.
Okay.
So this is another question about cost.
Okay.
You expect to pay more for higher assurance
Yes.
software. And if we take the cell 4 microkernel that you have figures for, there were 40 lines of proof for each line of code.
Yeah.
You had other figures for other parts of the systems. So I'm wondering, what is the cost for high assurance software in this domain? Now, obviously, the first time you do it, it's going to cost a lot more. But if you were to repeat the development of this kind of system, have you a feeling for how much the extra cost is?
I don't know, clearly higher, but in sometimes what a lot of the research challenges in HACMS are increasing the level of automation so that the costs go down. Also creating sort of a library of high assurance systems that you can reuse over and over again. So they're clearly always going to be higher, right? Because it's something else in addition to what was there before. But the hope is that it will come down dramatically. But we don't know yet, right? This is part of the tech transfer part of the chain. So it will clearly always be higher. But like the SEL4, they estimated that if they had to do it again, the cost would come down by 50% because the tool infrastructure was such that they wouldn't have to do that part again. So instead of costing 20 person years, it would have cost 11 person years to repeat the exercise. So that's a huge improvement in 4 years' time. So I don't know what the bottom is. I'm sure the bottom is higher than with doing it. Well, I step back there a second because in some sense we're not accounting properly, right? Because we're letting the sloppy people write the sloppy code and ship it, and we're charging them only for the time to ship the sloppy code. We're not charging them for all of the costs involved in people breaking in and having to clean up the systems, having to do all of that work. So if you did a proper accounting that included the cleanup costs and the security vulnerability costs, maybe the high assurance code in the end comes out to be equally competitive. But paying tomorrow versus paying today, right, is not necessarily the same as, yeah.
Hello, this is really impressive. On one of your slides, you had multi-core gulp written on it.
Oh yeah, that was part of the tech transfer.
And but on a slide before that, you had like the new version of the quadcopter that already had 2 processors. So what's scary about multi-core if you've already done it?
Right. So a lot of the formal methods results rely on code running on a single processor. So you can prove a result about the code running on a single processor and then prove system-wide things about how you put the code together. But all of the processors themselves might be coming multi-core in a way where you don't necessarily have control over that. And so the gulp part came from slides that Boeing put together about tech transfer. And they were talking about how they kind of want single processors, but they might not be able to buy them anymore, right? They just might not exist, and so like they only have multi-core processors that maybe they just configure to run in a single-core way. Like dealing with interleaving and things like that, there are lots more difficult technical problems that also happen.